Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss first conservative and non-conservative forces. Now, when a force is said to be conservative and when it is said to be non-conservative. I hope you know that, but still I will remind you. A force is said to be conservative. Definition. If a body is acted upon by a force whose work done on it body in a round trip is zero, it is said to be conservative. And for non-conservative forces, this definition: work done by this force on a body in a round trip is not zero. I repeat, if there is a body, it is acted upon by some force, and that force does work on the body. Now, the force is said to be conservative if work done by that force on a body in a round trip is zero. If the work done by a force on a body in round trip is not zero, it's called non-conservative force. What are the examples for conservative force? Examples are gravitational force is a conservative force. It's a conservative force. Electrostatic force is a conservative force. Here are examples. In case of non-conservative force, we have friction. Frictional force is a non-conservative force. It's one of the examples. So what's round trip? Round trip is if a body starts at point A, it moves to some other point B, and it comes back to A. This is called round trip. That means in round trip, initial position, X initial, if it stands for initial position, is same as X final position. So in round trip, the body comes back to its initial coordinate, initial position coordinate. Initial position and final position are same. That means, in other words, displacement is zero. Now, what is special about conservative forces? For conservative forces, we define quantity called potential energy, which we denote by U. Potential energy is the characteristic property of conservative forces. For non-conservative forces, there is no such quantity, right? For gravitational force, we define gravitational potential energy. For electrostatic force, we define electrostatic potential energy, right? So we define potential energy for conservative forces. I'm just reminding you certain things in order to move forward in my course. You must be knowing the expression if we have mass m1 and mass m2, point masses separated by distance r. Now this configuration of masses is associated with a potential energy U, which is called gravitational potential energy. The expression for that is minus G m1 m2 by r, where r is the distance between the masses, G is gravitational constant with value 6.67 into 10 raised power minus 11 Newton meter square per kilogram square. Newton meter square per kilogram square, right? So this is the expression for gravitational potential energy for two-point mass system, right? So gravitational potential energy is negative. That means the gravitational force is attractive, right? There is no gravitational repulsion. There's only attraction. So gravitational potential energy is only negative. Another thing you need to remember, when we say uh, gravitational potential energy of two-point mass system separated by distance r is minus g m1 m2 by r, it is assumed here that when these masses are infinitely apart, that means when r approaches infinity, then the potential energy in that configuration is assumed to be zero. I repeat, in this expression, it is assumed that when m1 and m2 are at infinite distance from each other, potential energy in that configuration is assumed to be zero, right? Similarly, we talk of electrostatic potential energy. It has the same expression like this. If we have two charges, Q1, Q2, point charges separated by distance r, then this point charge configuration possesses a potential energy which is given by 1 by 4 pi epsilon naught Q1 Q2 by r. can write it K Q1 Q2 by R, right? So this is the potential energy stored in this configuration of 2-point charges, right? K here is 1 by 4 pi epsilon naught. You know the values of K. K is Coulomb's constant. It is 9 into 10 raised by 9 Newton Coulomb square, Newton meter square per Coulomb square. You can find the unit from Coulomb's law. F is K Q1 Q2 by R square. So K will have unit in SI system Newton meter square per Coulomb square, right? That's not important. You can find that value. Similarly, you know the epsilon naught, it is called permittivity of free space. Now, in this expression also, it is assumed that if R tends to infinity, the potential energy of this 2-point charge system is assumed to be 0. So if Q1 and Q2 are at infinite distance from each other, the potential energy stored in the system is taken as 0, then the potential energy in this particular configuration when they are at r distance from each other is given by 1 by 4 pi epsilon naught Q1 Q2 by R or K1 Q2 by R. Now in case of gravitational potential energy, there is only attraction, so it is only negative. But electrostatic potential energy can be negative as well as positive. Because there are two kinds of charges, there are two types of electrostatic interaction. Charges can repel, charges can attract. They repel when they are like, they attract when they are unlike. Now, if two charges are unlike, that means this is positive, another one is negative, then the potential energy will turn out to be negative, right? And if they are like, force is repulsive, then potential energy will be positive. So positive potential energy characterizes repulsive force, and negative potential energy characterizes attractive force, right? Similarly, if we have more than two charges, if I have, for example, 3-point charges, Q1, Q2, and Q3, let the distance between 1 and 2 be R12, distance between 2 and 3 be R23, and distance between 1 and 3 be R13. It's R12, distance between 1 and 2, distance between 1 and 3 R13, distance between Q2 and Q3 R23. This system of charges also possesses the potential energy. How to get that expression? You have to use this expression 1 by 4 by epsilon naught Q1 Q2 by R for each pair of charges, each unique pair of charges. So it will have three terms. So potential energy associated with the system of charges will be given by 1 by 4 pi epsilon naught Q1 Q2 by R12 plus 1 by 4 pi epsilon naught Q1 Q3 by R13 plus 1 by 4 pi epsilon naught Q2 Q3 by R23. 1 by 4 pi epsilon naught Q1 Q2 by R12 plus 1 by 4 pi epsilon naught Q1 Q3 by R13 and Q1 Q2 Q3 term is there 1 by 4 pi epsilon naught Q2 Q3 by R23. Similarly, if we have many masses, then you can use this expression for each pair of unique masses and add those terms to get the gravitational potential energy of that particular configuration of masses. Let me show you some example on gravitational potential energy. So I write here sample, or let me use next page, or let me write here sample problem 1. The problem says 2 protons in the nucleus of a uranium U-238 atom are 6 femtometer of Fermi apart. What is the potential energy associated with the electric force that acts between these two particles. I repeat the question. 2 protons in the nucleus of a U-238 atom are 6 femtometer apart. What is the potential energy associated with the electric force that acts between these two particles? Two protons, proton, it has charge of 1e, and the force between protons would be electrostatic in nature. So I will use the expression, this one, Q1 Q2 by R, or 1 by 4 pi epsilon naught Q1 Q2 by R. The solution will go like this. Potential energy associated with electrostatic force acting between the two protons within the uranium 238 atom will be given by this expression, 1 by 4 pi epsilon naught Q1 Q2 by R. So value of 1 by 4 pi epsilon naught, which is K, is approximately what? 9 into 10 raised by 9 Newton meter square per coulomb square. This is value of 1 by 4 pi epsilon naught. Then I have Q1, Q2. No, Q1 is equal to Q2. Charge on the protons is same, as both are equal to E, which is 1 point. 602 into 10 raised power minus 19 coulomb, right? Q1, Q2 is same, E. Charge on each proton is E, which is having value 1.602 into 10 raised power minus 19 coulomb. So I substitute here 1.602 into 10 raised power minus 19 coulomb, then I square it, because here I will have Q1E, Q2E, then it will become E square, and downstairs I have distance between the protons in the nucleus, which is 6 femtometer. 1 femtometer or 1 Fermi is equal to 10 raised power minus 15 meters. So here I have to substitute 6 femtometer, that is 6 into 10 raised power minus 15 meter, right? So when I solve it, it will turn out to be 3.8 into 10 raised power minus 14 joule. 3.8 into 10 raised power minus 14 joule. You can check it. And if I convert it into electron volts, it will be 2.4 into 10 raised power 5 electron volts, or I can write it to 40 kilo electron volts. So 3.8 into 10 raised power minus 14 joule, which is 2.4 into 10 raised power 5 electron volt, or which is equal to 40 kilo electron volt. Must be knowing 1 electron volt is 1.602 into 10 raised power minus 19 joule. There is a convergent relationship between electron volt and joule. Electron volt is another unit of energy. From this you can convert from joule to electron volt, right? And you also know that 1 kilo electron volt is 1000 electron volt, that is 10 raised to 3 electron volt. So we have used that fact here. So this way we solve these simple problems related to potential energy, and you must be noticing that the electric potential energy here is positive, because the nature of electrostatic force between the two protons in the nucleus is repulsive in nature, right? Then there is another quantity, electric potential. Electric potential. We define that let me discuss that. Electric potential is a scalar corresponding to a vector electric field, right? We have already discussed the idea of field. We know if we have, for example, a charge, if we have a charge, for example, positive point charge, then surrounding it there is an electric field, which we have already represented by, which we already know, it can be represented by the electric lines of force. And how we define the electric field, we say if we take some point P in the neighborhood of this charge, which we call source charge, place a test charge there, Q naught, which is small positive charge. We find force between Q and Q naught, then divide that force by test charge. That will give me the electric field E at point P, right? Surrounding any charge, there exists this vector field called electric field. Now we define another quantity, electric potential, which is a scalar, as I said, the scalar corresponding to the vector electric field. You can interpret the effect of charge on the surrounding space by using the idea of electric field, or equivalently by using the idea of electric potential, right? See, we obtain electric field from force. Now, electric potential energy is a scalar corresponding to electric force, right? And electric potential we denote by V is a scalar corresponding to electric field. Now, how we obtain it, we write, similarly we will have, it's not necessary we have a single charge, we can have many charges. So suppose I have many charges, Q1, Q2, Q3, 1, 2, 3, Q4. I can have any number of charges. Now I select some point P here, right, in the neighborhood. So what we do, let this be the boundary, that means here is infinity. So I have a test charge at infinity, right? Now this system of charges will have some potential energy, right? And we can find that by using this formula I've already discussed, K Q1 Q2 by R. We have to see how many unique pairs of charges we can frame. Incidentally, what is the number of terms if we find the electric potential energy of 4-point charges? For 3, it was 3 terms. If I bring a fourth charge, that fourth charge will interact with all these 3 charges. So there will be additional 3 terms. That means for 4 charges, I will have 6 terms. So there will be 6 terms like this in the potential energy of this 4 charge system. But this Q naught will not contribute to that potential energy because it is at infinite distance from these charges. We have said when charges are at infinite distance from each other, potential energy corresponding to that configuration is 0. When I take this test charge and place it point A, understand it. I will repeat it. I said, let me use this code. I said first, this test charge is at infinity. This system of charges has certain potential energy. When I take test charge to point P, now the potential energy of the system will change by some amount, because now test charge will also contribute, right? Now if the change in the potential energy is UP, and the change and the potential energy when I take test charge to point P is UP. Then the electric potential at point P, VP, is by definition UP by test charge, right? I repeat, I have a collection of, let me use this spotlight. So I have a collection of point charges. I have shown here 4 point charges, but it can be any number of charges, right? Now I wish to determine the electric potential at point P, which is a point in the neighborhood. So what I do, I place it, I bring a test charge from infinity to point P, right? So in that process, what happens? The potential energy of the system changes from zero. When I say from zero, that is of this particular contribution of this test charge term, right? It changes from 0 to value UP. UP is what? It is a contribution of the test charge. First, contribution of the electric potential energy to by the test charge was 0 because it is at infinite distance from the charges. Then when I take it to point P, now it will contribute. So potential energy has changed from 0 to some value, that is UP. So I divide that potential energy by test charge to get the potential at point P, right? Let me bring my pen back. To do this. Let me fix this. What happened to my pen? Okay. So electric potential is defined this way. So it's a scalar quantity. It has unit of joule per coulomb, which is called volt. 1 joule per coulomb is 1 volt. It is independent of the test charge because this potential energy change will contain the this potential energy change will contain test charge. When you divide that by test charge, electric potential will not contain test charge, right? So every charge will have electric potential surrounding that charge. You need to remember the potential. When I say potential, that is electric potential now. The potential near an isolated positive charge is positive. The potential near an isolated positive charge is positive. The potential near an isolated negative charge is negative, right? So if I have a positive charge Q at all points P, Q, any point surrounding it, potential is positive. Similarly, if I have a negative charge Q minus Q, then at all points in its neighborhood, potential is negative, right? Now, what is the expression for electric potential? I will give you that expression. Expression for electric potential due to a point charge. If I have a positive point charge Q, select point P, r distance from it, then the electric potential at point P is 1 by 4 pi epsilon naught Q by R. This is the expression. Now remember here, it is also assumed in this case also that if point is at infinity, then potential is taken as 0. If R tends to infinity, potential is taken there as 0. Then this expression is valid. So if Q is positive, potential is positive. If this charge is negative, then potential everywhere surrounding it will be negative. And if for positive charge, if R decreases, potential will increase. So if you move closer to a positive charge, potential increases. But in case of negative charge, if R decreases, it will become more negative. That means if you move closer to a negative charge, potential will decrease. If you move away from the negative charge, potential will increase. If we move closer to a positive charge, potential will increase. If we move away from a positive charge, potential will decrease, right? Similarly, if I have many charges, if I have charge Q1, charge Q2, charge Q3, and I have a point P, I have to find potential at point P. What you do, you find potential due to charge 1 using the expression 1 by 4 by epsilon naught Q by R. Then find potential due to charge 2, assume Q1 and Q3 are absent. Then find electric potential at point P due to charge 3, V3, assume other two charges are absent. Then add those scalars to get the resultant electric potential at point P. So this means that superposition principle is applicable to electric potential, right? Sometimes, let me move back. So we defined the electric potential. We were moving test charge from infinity to point P. Sometimes both the points are within the field, electric field, and we write this expression. We write delta V is equal to VB minus VA, which is UB minus UA by Q naught. It simply means if there is some electric field, let me use some color here. It simply means if there is in certain space an electric field and we select in that electric field 2 points A and B with this point A, this point B. This point A has potential VA. This point has electric potential VB. Now, if you move the test charge from A to B, we move the test charge from A to B, Q naught, then the change in electric potential, delta V, VB minus VA will be equal to change in potential energy per unit test charge. UB and UA is what? Is the UB is the electric potential energy of the configuration when Q naught is placed at B. UA is the electric potential energy when test charge is placed at A. Right? So change in potential is change in potential energy per unit test charge. And we also write it sometimes minus WAB by Q naught. It's another thing where WAB is what? WAB is the work done by the electric field as test charge is moved from A to B. Right? I repeat here, WAB is the work done by the electric field as test charge is moved from point A to point B. Negative is because of the definition. Change in potential energy is by definition negative of the work done by the conservative force involved. Here the conservative force involved is electrostatic force, right? So I will give you some homework related to it. Homework. Question 1. First question is, in the system shown in figure A, figure A is this figure. I have 3-point charges. A simple question. Now, Q1 and 2 are separated by R12. Q1 and 3 are separated by Q13, and Q23 are separated by R23. So this is my charge. This is my figure A. Let me move back to questions. So I have 3-point charges, Q1, Q2. separated by R12, 2, 3 separated by R23, 1, 3 separated by R13. The question says in the system shown in figure A, assume that R12 is equal to R13 is equal to R23. R12 is equal to R13 is equal to R23, all equal to D equal to 12 centimeter, and that Q1 is equal to plus Q, Q2 is equal to minus 4Q, and Q3 is equal to plus 2Q, where Q is equal to 150 nanocoulomb, what is the potential energy, electric potential energy, right, of the system? It's very simple. Q1 is plus Q, Q2 is minus 4Q, and Q3 is plus 2Q. While Q is 150 nanocoulomb, you must be knowing 1 nanocoulomb is 10 raised power minus 19. Oh, sorry, 10 raised power minus 9. 1 nanocoulomb is 10 raised power minus 19 coulomb, not 19. 1 nanocoulomb is 10 raised power minus 9 coulomb. So you have to calculate the potential energy of this system, right? Let me find question for you. Okay, you have another question. An alpha particle Q equal to plus 2e in a nuclear accelerator moves from one terminal at a potential of VA equal to plus 6.5 into 10 to the 6 volt to another at a potential of VB equal to 0, part A. What is the corresponding change? What is the corresponding change in the potential energy in the potential energy of the system. Part B, assuming the terminals and their charges do not move, and that no external forces act on the system. What is the change? What is the change in kinetic energy of the particle, alpha particle, right? I repeat the question. An alpha particle which has a charge of Q equal plus 2e, where you know E is the charge on proton, 1.602 in 10 is per minus 19 coulomb. In a nuclear accelerator, moves from one terminal at a potential of V equal to 6 plus 6.5 into 10 is per 6 volt to another at a potential of VB equal to 0. Part A, what is the corresponding change in the potential energy of the system? Part B, assuming the terminals and their charges do not move and that no external forces act on the system, what is the change in kinetic energy of the particle? This is all for today. Do your homework, don't waste your time, and don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.